Chapter 3 Finite Element Method. The analysis of design of product is prime field in mechanical engineering. This chapter introduces finite element method as design analysis tool. One-dimensional elements in FEM are discussed in detail so that study of FEM can be carried out at ease. The truss problems are also introduced as a special case of one-dimensional element. Learning objectives. Number 1. Learners will be able to understand the various stages of the finite element method and its application in the analysis of the design of the product. Number 2. Learners will be able to perform stress analysis of simple parts and truss using a one-dimensional element. Number 3. Learners will be able to develop a computer program for stress analysis of simple mechanical parts using the finite element method. Para 3.1 Introduction. In the design of the product, the safety of the product is essential. This is achieved by using a simple principle in machine design, that is, stress developed in part should be less than allowable stress of the material. The design of the mechanical part can be refined considering stress all over the part. For example, in the design of the shaft, the diameter of the shaft is decided considering the maximum stress induced in the shaft. It is possible to reduce the diameter of the shaft in other regions of the shaft where stress is less than maximum stress. By reducing the diameter at a separate section, it is possible to modify the design of the shaft. Refer figure 3.1. Stress distribution over the whole part can be found out using the finite element method. It is defined as the numerical method to find the value of the field variable using approximation. The field variable can be displacement, temperature, etc. The approximation used in the finite element method is valid in engineering sciences, which will be explained later. There are 6 stages in the finite element method. Number 1, discretization. Number 2, selecting solution approximation. Number 3, to establish a matrix equation. Number 4, assembly. Number 5, finding the unknown. And number 6, interpretation. Para 3.1.1 Discretization. This is the first and the most important stage of the finite element method. The complete body, hence onward called continuum, is divided into elements and nodes. The connectivity of elements is through nodes. In figure 3.2, the cantilever is discretized into 12 elements and 21 nodes. The value of the field variable, that is displacement, is found out at nodal points. Based on the displacement at nodal points, it is possible to get the value of strain and stress over the element domain. It is thus clear that the smaller the size of the element, the more accurate solution can be obtained. It is therefore desired that continuum must be divided into as many numbers of elements as possible, and the elements are non-overlapping. Para 3.1.2 Selecting solution approximation. It is possible to find strain or stress by defining the function in which input variables will be displacement at the nodal points. The function or expression is approximate because using the value of the displacement at nodal points, the strain of any point over the element domain is found out, not directly finding the value of strain at the point of interest. The expression or the function to be selected is polynomial because it is easy to integrate or differentiate. This is the only stage of the finite element where the approximation is involved. Para 3.1.3 To establish a matrix equation. It is necessary to know the value of the displacement at nodal points. This can be done by establishing an equilibrium equation in which displacement is the parameter. There are 4 methods by which such an equation can be established. Number 1, direct method. Number 2, variational principle. Number 3, weighted residual method. Number 4, energy method. Para 3.1.4 Assembly. The equilibrium equation for all the elements is assembled to form a global equilibrium equation. The global equilibrium equation consists of the displacement parameters of all the nodes of the continuum. Assembly of all the elemental equation is necessary as nodes are shared by the elements to form a global equilibrium equation. Para 3.1.5 Finding the unknown. The global matrix equation is solved using the Gauss elimination approach and applying boundary conditions to get the value of the displacement at global nodes. Using the value of displacement at the nodal points, derivatives of displacement, that is strain or stress over the element domain, can be found out. Para 3.1.6 Interpretation. The result obtained using the finite element method needs to be interpreted by the design engineer for the modification of the design. This is the most critical stage of the finite element method, as treating the finite element method as a black box is a dangerous and risky process. Para 3.2 Principle of Minimum Potential Energy PMPE. Using PMPE, it is possible to derive the equilibrium equation in which displacement forms as one of the parameter. It is expressed as, for any elastic body, total potential energy is minimum if it is in equilibrium. The total potential energy is defined as the summation of strain energy and work potential. Consider a spring subjected to force P. Let U be the displacement of the spring and K be the stiffness of the material of the spring. Refer figure 3.3. The strain energy developed in the spring is given as 1/2 Ku square. Force P is getting displaced by U units. Potential energy or work done due to P is called work potential. It can be written as work potential equal to P into U. Total potential energy can be written as total potential energy equal to strain energy plus work potential. That is, M equals to 1/2 Ku square minus Pu, where M represents total potential energy. For total potential energy to be minimum, we have dm by du equals to 0. That leads to Ku minus P equals to 0, and therefore Ku equals to P. If the stiffness of the material and force are known, displacement can be found out using the equation Ku equals to P. To find the displacement at nodal points on the continuum and considering an analysis of the element on the continuum, the equation can be written in matrix form as K matrix into U matrix equals to P matrix, where K matrix is a stiffness matrix representing the stiffness of element, U matrix is the displacement matrix representing the displacement of nodes, and P matrix is force matrix representing forces acting on the element. Para 3.3 Types of elements. The elements are classified under three categories. Number 1, one-dimensional element. Number 2, two-dimensional element. Number 3, three-dimensional element. One-dimensional element. In one-dimensional element, displacement of the node takes place in one and the same direction. One-dimensional element is also called as a bar element or line element. Refer figure 3.4. The spring which is attached to the free end of the cantilever can be discretized as one-dimensional element. Refer figure 3.5. Two-dimensional element. There are two types of two-dimensional element, namely one triangular element, number 2 quadrilateral element. The triangular element consists of 3 nodes, while the quadrilateral element consists of 4 nodes. Refer figure 3.6. The triangular element is the basic element because the quadrilateral element can be considered as the combination of two triangular elements. The displacement of nodes of the two-dimensional element is expressed in two mutually perpendicular directions. The quadrilateral has simple geometry, hence it is preferred over the triangular element. The two-dimensional element is used in the problems of the plane stress and plane strain. Three-dimensional element. There are three types of the three-dimensional elements, namely number 1 tetrahedron, number 2 prism, number 3 hexahedron. Refer figure 3.7. The displacement of the nodes of the three-dimensional element is expressed in three mutually perpendicular directions. Three-dimensional elements are used in engineering problem where the solid body, that is 3D body, is considered for analysis. Para 3.4 Shape function. To get strain and stress over the element domain, the function is selected where the displacement of the nodes is the input. The polynomial expression is selected to get such value. Consider an element E as shown in figure 3.8. The element is shown with the two nodes having displacement u1 and u2. P is any point on the element which is shown at x distance from the node having displacement u1, and L is the length of the element. The displacement of any point P over the element domain can be written using the polynomial expression in terms of the geometrical position of the point over the element domain, that is x. The expression for the displacement of point P, that is u, using linear polynomial expression can be written as u equals to alpha 1 plus alpha 2x. This equation u equals to alpha 1 plus alpha 2x is called displacement function. We know at x equal to 0, u is equals to u1. So u1 is equals to alpha 1. At x equal to L, u is equal to u2. L is the length of the element and therefore u2 is equals to u1 plus alpha 2L. Therefore, alpha 2 is equals to U2 minus U1 upon L. Substituting the values of alpha 1, alpha 2, we have U is equals to 1 minus x by L into U1 plus x by L into U2. This can be expressed as U equals to N1 U1 plus N2 U2, where N1 is equals to 1 minus x by L and N2 is equal to x by L, where N1 and N2 are called shape functions of point P. Every point on the element domain has a unique shape function. It is important to note that there are two shape functions, that is N1 and N2, for the one-dimensional element. This is because one-dimensional element has a minimum of two nodes. It can be proved that N1 plus N2 is equals to 1. It is thus clear that if one parameter of the shape function is known, others can be found out. That is, N1 is equals to 1 minus N2 or N2 is equal to 1 minus N1. The variation of N1 and N2 over the element domain can be seen as indicated in figure 3.9. Thus, shape functions are used to find the displacement of any point over the element domain. Displacement of any point over the element domain can be written using the shape function as U equals to N1 U1 plus N2 U2. If U1 and U2 are replaced by Q1 and Q2, then it can be written as U equals to N1 Q1 plus N2 Q2. Para 3.5. Elemental strain displacement matrix. The strain and hence the stress at a point in the element can be found out, and it is expressed as epsilon equal to BQ, where B is equals to 1 upon L minus 1 1 and Q is equals to Q1 Q2, where B is called the elemental strain displacement matrix and Q is the elemental displacement matrix. It is clear that strain at any point over the element domain is the same. Such elements are called constant strain element. If the size of the element is very small, then the assumption that strain is constant over the element domain is accepted. The constant strain is obtained because of the linear approximation used in the displacement function. Refer figure 3.10. If the strain is known, stress can be found out. Sigma equals to E into epsilon. Sigma equals to EBQ. The stress over the element is also constant. From the expression of U, matrix equation can be written as U equals to N1 Q1 plus N2 Q2, U equals to NQ, where N is N1 N2 and Q is equal to Q1 Q2. Para 3.6. Type of forces. There are three types of forces considered in design analysis using finite element method. Number 1, body force. Number 2, traction force. Number 3, point force. Body force. The force which is distributed uniformly over a body is called body force. The weight of the body is the example of body force. It is expressed as force per unit volume, that is density. Traction force. The force which is acting over the surface area of the body is called traction force. It is expressed as force per unit area. The friction force, viscous force, drag is the example of traction force. Point force. The force which is applied by the external agency on the body is called point force. It is expressed in absolute unit of forces, that is Newton. It is important to note that force must be applied at the nodal points. If at the application of the force, the node is not present, then create the node at that point. Consider a one-dimensional element as shown in figure 3.11. Q1, Q2 is the displacement of nodes 1 and 2, while F1, F2 are forces at nodes 1 and 2. Using the principle of minimum potential energy, the matrix equation can be written as K into Q equals to F, where K is the elemental stiffness matrix and Q is the displacement matrix. F is the elemental force matrix. It is clear that Q and F are column matrices. The elemental displacement matrix consists of displacement at nodal points and it is given as Q equals to Q1, Q2. Similarly, the force matrix, that is F, consists of forces at nodal points and it is given as F equals to F1, F2. The order of Q and F is the same, that is 2 by 1. Hence, elemental stiffness matrix K is 2 by 2 matrix, that is a square matrix. Para 3.7. Elemental stiffness matrix. To find the expression of elemental stiffness matrix, the concept of strain energy is used. The elemental stiffness matrix can be written as Ke equals to Ae by L 1 minus 1 minus 1 1. Para 3.8. Elemental force matrix. The elemental force matrix consists of two components. Number 1, body force component. Number 2, point force component, neglecting the traction force component. Let P1 and P2 represent the point forces at nodes 1 and 2. Therefore, the point force component of the elemental force matrix can be written as P1, P2. The body force of the element will be AL rho, where rho is the weight density. As it is necessary to apply the force at the nodes, body force is equally divided at the two nodes, and hence the body force components of the elemental force matrix can be written as AL rho by 2, AL rho by 2. The elemental force matrix can be written as P1 plus AL rho by 2, P2 plus AL rho by 2. The elemental matrix equation can be written as AE by L 1 minus 1 minus 1 1 into Q1 Q2 equals to P1 plus AL rho by 2, P2 plus AL rho by 2. Para 3.9 Assembly. Using the elemental matrix equation, it is not possible to get displacement at the nodal points of the element because the node is shared between two elements. In order to find the displacement at nodal points, it is necessary to apply the matrix equation to continuum, which can be solved to get displacement at nodal points. Consider the step bar as shown in figure 3.13. In this figure, Q1, Q2, Q3, Q4 represent the displacement of the global nodes, that is nodes on the continuum, 1, 2, 3, 4 respectively. F1, F2, F3, F4 are the forces at the global nodes 1, 2, 3, 4 respectively. P1 is the applied force at node 4. The matrix equation for the continuum using the principle of minimum potential energy can be written as K equals to QF, where K is called global stiffness matrix, Q is the global displacement matrix, and F is the global force matrix. Q is represented as Q1, Q2, Q3, Q4. The order of Q is 4 by 1. As orders of Q and F are same, F can be written as F1, F2, F3, F4. It is clear from the matrix equation that the order of the global stiffness matrix is 4 by 4. It is now necessary to know the global stiffness matrix, which can be obtained by assembling the elemental stiffness matrices of elements 1, 2, 3. So K global will be equals to K1 plus K2 plus K3. The global matrix equation can be written using the global stiffness matrix. This matrix equation leads to 4 algebraic equations with 4 unknowns, that is Q2, Q3, Q4 and R, that is the reaction force at nodes, that is F1. The above equation can be solved by applying the boundary condition. In the problem, the boundary condition is Q1 equals to 0 as node 1 is fixed. This can be solved using Gauss elimination method. Thus, displacement at nodal points can be found out. Note, the boundary condition means knowing the value of the displacement of the nodal points before the solution. The strain and stresses of the element can be obtained using the formula epsilon equal to BQ and sigma equals to EBQ. Para 3.10 Truss. The problem of trusses, that is finding stresses induced in the truss member, can be solved using the finite element method. The truss is discretized into elements and nodes by considering a truss member as the element and joint as the node. The truss shown in figure 3.14 is discretized into 7 elements and 5 nodes. As the force on the truss is always applied at the joints, that is node, the finite element method can be used. The element is considered to be one-dimensional element. The displacement of the nodes of the element is not taking place in one and the same direction because of the different orientation of the truss members. But as truss member is subjected to tensile or compressive load, the displacement of the nodes of the element can be considered to be along the axis of the member, that is in one and the same direction. The element of the truss therefore considered to be a spatial one-dimensional element. Q1 dash and Q2 dash are considered to be displacement of nodes if the truss member is subjected to tensile or compressive load, that is Q dash is equals to Q1 dash Q2 dash. Q1, Q2 represent the component of the displacement that is taking place at node 1. Similarly, Q3, Q4 represents the component of the displacement that is taking place at node 2. Thus, Q is equals to Q1, Q2, Q3, Q4. Q represents the displacement matrix when a component of the displacement at nodes 1 and 2 are considered. Q dash is important because the procedure of one-dimensional element can be applied to solve the truss problem. The relation between Q dash and Q can be established as follows. Consider the element E subjected to force. Let 1 dash and 2 dash be the displaced position of nodes 1 and 2. The displacement Q1 dash of node 1 can be expressed in terms of Q1 Q2 as Q1 dash is equal to AB plus BC, that is equals to Q1 cos theta plus Q2 sin theta, where theta is the angle made by the element with positive x-axis. In order to find the cos theta and sin theta, the concept of direction cosines can be used. For element, the direction cosines can be expressed in terms of L and M as L is equals to cos theta equals to x2 minus x1 upon LE, M is equal to sin theta is equals to y2 minus y1 upon LE, where LE is equal to under root of x2 minus x1 whole square plus y2 minus y1 whole square. It is clear that direction cosine of the member can be found out if the coordinates of the nodes of the elements are known. Thus, it can be written as q1 dash is equal to q1l plus q2m. Similarly, for node 2, it can be written as q2 dash equal to q3l plus q4m. Equations can be written in matrix form as q dash is equals to lq, where L is equals to Lm0000Lm, where L is called as linking matrix. Elemental stiffness matrix. We know the expression for elemental stiffness matrix for one-dimensional element K equals to AE by LE 1 minus 1 minus 1 1. This expression can be used when the displacement at the nodes is expressed in the form of local coordinates, that is q dash. It is necessary to know the expression for the elemental stiffness matrix when the displacement is expressed in the global coordinate form, that is q. It can be shown that Ke is equals to L transpose K into L, where Ke is called elemental stiffness matrix when the displacement is expressed in Q1, Q2, Q3 and Q4. Ke can be written as AE upon LE, L square Lm minus L square minus Lm, Lm m square minus Lm minus m square, minus L square minus Lm, L square Lm, minus Lm minus m square, Lm m square. Using elemental stiffness matrices, it is possible to get global stiffness matrix by using assembly procedure. Refer figure 3.17. The order of the global stiffness matrix is 2n by 2n, where n is the number of global nodes. It is thus clear that global stiffness matrix of the order of 2n by 2n can be obtained by assembling element stiffness matrices of the order 4 by 4. Displacement at the global nodes can be found out using the equation as obtained by principle of minimum potential energy Kq equals to F, where Q represents global displacement matrix of the order 2n by 1, F represents the global force matrix of the order 2n by 1. The strain and the strain of the element can be written as epsilon equals to 1 upon Le minus L minus M L M into Q, and the stress can be written as sigma equals to E upon Le minus L minus M L M into Q, where sigma is stress and epsilon is strain. Para 3.11 Introduction to two-dimensional finite element method. In 2D finite element method, triangular and quadrilateral elements are studied. Out of these, triangular elements is more basic and fundamental, and hence it is studied in more detail. Consider a triangular element as shown in figure 3.19. The displacement of any point P can be expressed in terms of nodal displacement as U equals to N1 Q1 plus N2 Q3 plus N3 Q5, and V is expressed as N1 Q2 plus N2 Q4 plus N3 Q6, where N1, N2, N3 are called shape functions. Equation is called as displacement function. It is clear from the displacement function that if the shape functions of any point is known, then the displacement at the point can be found out in terms of nodal displacement. The values of the shape functions at any point can be found out using the concept of area coordinate. Area coordinate. The area coordinate at any point P over the element can be found out by joining point P to the nodal point. The triangular element is divided into 3 subtriangles. The areas of the 3 triangles are indicated as shown in figure 3.20. The shape functions of the point P can be defined as N1 equals to A1 upon A, N2 equals to A2 upon A, and N3 is equals to A3 upon A, where A1, A2, A3 is equals to A. It is clear from the above expression that N1 plus N2 plus N3 is equals to 1. Therefore, N3 is equals to 1 minus N1 minus N2. It means if any 2 shape functions are known, third can be found out. The shape functions for the nodal points are indicated in figure 3.20. To obtain displacement and nodal points, the expression for the continuum can be expressed as Kq equals to F, where K is global stiffness matrix, Q is the global displacement matrix, and F is global force matrix. The order of the global displacement matrix is 2n by 1, where n is the number of nodes. The order of F is the same as Q, and hence the order of K is 2n by 2n. The equilibrium equation For the element can be written as KQ equals to F, where Q is the displacement matrix of the order of 6 by 1. The order of elemental stiffness matrix K is 6 by 6. It is clear from the above expression that the global stiffness matrix of the order 2n by 2n can be obtained by assembling the elemental stiffness matrices of the order 6 by 6. The process of assembling is quite complex and it can be executed only with the help of computer. Questions. Number 1. Explain in brief the basic steps of finite element analysis. Number 2. What are one-dimensional, two-dimensional and three-dimensional elements used in the discretization process? Number 3. Explain the concept of shape function. Number 4. Explain the potential energy approach used in the finite element method. Number 5. Explain the process of assembly of element matrices as applicable in the finite element method. Number 6. Explain in brief the concept of finite element analysis, FEA, and finite element modeling. Number 7. Why is the element connectivity table important in the analysis of truss? Number 8. Differentiate between plane stress and plane strain. Fieldwork. Visit any industry which has a separate design department and design engineer employed in it. Discuss the use of FEM in the design of mechanical part in the industry with the design engineer. Present your work in the class and compare your presentation with the presentation of your colleagues. Number 2. List down the ready-made software used in the FEM and associated name of the company.